So hi Johnny, nice to see you from Barry.
Hi Harriet, how are you doing?
I'm pretty good, thanks. Yeah,
Good. Enjoying the long weekend?
yeah. Still,
Excellent.
working on machine learning even.
I know, yeah, we're such geeks. We're such geeks that
Yeah,
over the long weekend we're still while you're at the cottage, we're still running um, these notebooks.
collab books, I know.
Yeah, it's like so nerdy.
Yeah. So would you like to go through maybe first a few chunks of the collab?
Sure. So I just want to describe to you what I'm trying to do here.
Mm,
We decided last time when we meet up that we would be using some Yelp dataset,
yeah,
and these are Yelp reviews.
yeah.
So what we're trying to do is trying to use the review text, the comments in
Mhm.
particular, to predict whether this is a positive or a negative experience.
Yeah,
For those people who might not be familiar with Yelp, it's a review service popular in North America. They use user-generated reviews to rank, uh, locate small businesses like restaurants, cafes, laundromats, and um, so they have a lot of user data that is being generated uh,
Mhm.
on small businesses in North America. Well, our task is to uh, take the fastai uh, example and use this Yelp data set on it to see if we can uh, recreate the results, right,
Right,
of fastai.
right. So, which Fast AI already try this set of framework on the IMDb dataset, right? So,
That's correct.
actually,
Yeah.
I see that the IMDb dataset is actually being used to evaluate different progress of the latest model. So, for say, you will see that on GitHub, like when people actually publish different new methods in NLP, they actually all create a table saying, like for say the most recent one, which is the XLNET, that claim that they beat BERT, and then they actually will create a row of metric that in which data set they beat BERT. So for say usually IMDb data set is one of the data set that they will need to demonstrate that if they excel the older previous method. And another one, I do also see people including Yelp as well as one of the comparison of different methods. And then it's just like computer vision, like they also evaluate the newer invention on at least like on the same basis of data set to compare to previous model. Yeah, it's just something I would like to add.
Right, right. Yeah, so just a quick illustration of how we're going to accomplish this. So the way how it works is we're not going to train a model from scratch. We will be using a technique called transfer learning, um, and we will be using this data set, which is wikitext 103. So it's trained on the corpus of Wikipedia. It creates something, it creates a language model for the wikitext. Um, and then we will fine tune that model. In the FastAI model, what they are fine tuning is to the IMDb, basically movie reviews. In our case, we will be using Yelp reviews. So we want to fine tune it with our Yelp corpus to create a language
Right.
model for Yelp specific, basically for the Yelp specific data set. And then
Mhm.
once we have that language model, we will again train the model to classify Yelp reviews to identify
Mhm.
whether a piece of text is coming from a positive experience or a negative
Yeah.
experience.
Right.
Yeah, so I think this diagram demonstrates that.
Right, so for this diagram, the previous two are within the encoder part, and then the last one is in the decoder part. So, so the first one, the gray one, is the pre-trained model that we downloaded, and then the second one is using our own. So usually that pre-trained model is being generated on some really huge corpus, usually being a Wikipedia set or like Google News. That's how they generated the word2vec embeddings. And then the second one is using our small data set to fine tune, to just update the parameters of the pre-trained encoder part of the pre-trained model. So that's called the language model to fine-tuning. And then the later part is the third one. The third diagram is actually we detach the decoder part of the pre-trained model, and then replace it with our own decoder to get the classification and then fine tune the parameters at that stage. That's my
Exactly. Yeah.
understanding. Yeah.
Yeah. Yeah. And the advantage of doing this obviously is because there are a lot of pre-trained models out there already that uh, companies like Google, Facebook, Microsoft, these large companies, they have already spent a lot of resources on training a huge corpus like the Wikipedia model. So you're able to sort of take it off the shelf and not have to spend too much computing resources on fine-tuning a language model. And Yelp is only one of the examples. Another example that we are both interested in would be something like medical records, right? Because on medical record, they will have their own vocabulary, and we can leverage the wiki text language model or any other model to do the fine tuning so that we don't so that speeds up the training time and also give really good results.
Yeah. So in this case, this set of method framework is actually a model independent, which is agnostic of the model. So therefore, like we can basically use this framework of method on any pre-trained model, as Johnny mentioned. So therefore, we will also use this fine-tuning method on BERT as well to compare with the default, the sequential RNN model, AWD LSTM. And another thing I would like to add as well is when you see that the previous two arrows, so when you are actually fine-tuning, because you download that pre-trained model, so usually that encoder structure architecture is something that you cannot modify. So for example, what I mean by that is, so sometimes let's say that you want to also add metadata instead of the text data. So for say, in addition to the text data that you have, you also want to add, for say, demographics data or environment data or any other external factors. Usually, that part of the encoder architecture you cannot modify because it's that thing that you downloaded. But instead, you can actually modify the decoder part, which is the third arrow, which is the classifier part. So usually that's why if you talk to people about, for say, when they are building like a recommender system using these encoder decoder structure. So when you need to add the metadata, it's usually in this third component. So in this decoder part, it's usually the second last layer before the softmax activation layer. So that's where you add the metadata as well. So that's the part that you can modify. Yeah, sorry about babbling.
That's fine. Yeah, it's good to hear some more in-depth explanation as I learn from you all the time.
Okay.
Okay, so let's look at the notebook because this is where all the action is. So I'm using a Google Colab, which is really great because it's extremely fast to get set up. They're pretty generous with their compute as well. So because we're using fastai, so we need the first line here, which will download the fastai library.
Mm-hmm.
And then we do a whole bunch of imports, and this is necessary because Harriet and I, we're sharing a Google Drive folder. So this allows us to connect that drive to this notebook. That way we can save any intermediate results, we can save any models, or we can pull in any data sets that we choose to drop into our Google Drive directory. So this is the part that that is being set up. It's actually really convenient because then you can just drop things into a folder. As you can see here on this here, what we're trying to do is we're trying to so we actually downloaded the Yelp Review dataset. Actually, Harriet did it, and he dropped it into a folder, and I'm able to just pull it up from our Google Drive, and immediately put that into a Panda data frame. So so this line here, so the reviews is a Panda data frame where we read the CSV, which is a yelp.csv file, which resides in the Google Drive. And so now what we can just do a quick exploratory look at the data set. So we have what we have here are reviews. What I'm trying to do here is to group them by stars. So for a Yelp review, it can either be a 1-star, 2-star, or all the way up to 5 stars. So I just want to have a quick look at the distribution of the different ratings. And we can obviously see that 4 or 5 stars means they're good. It's interesting because some people actually they will actually thought it's in the reverse, but the more stars you get is actually is better on Yelp. So as you can see, a lot of people are quite generous in giving out their stars, because if we look at so the top 2, the 4 and 5, they're actually the majority of the reviews, and then the 1 star, 2 stars, and 3 stars are actually less than a half, right? Right. So yeah, so what I did here was I just just jot down some quick notes. Realized that 68% of the reviews are 4 or 5 stars, and so Harriet and I had a discussion, and we thought that, oh, if that's the case, there's a highly imbalanced data set here. So what could we do? We decided to actually compress that and to look at just the 1 star. So what we want to do is we want to compress the 4 classes, the 5-star, 4-star, 3 stars, and 2 stars, compress all of them into one class, and try to detect only the 1 star.
Not generous people.
Yeah, the horrible locations, right? The horrible restaurants, the really bad coffee shops.
Yeah.
That
you want to avoid at any
cost. That you want to avoid. Exactly. That you want to avoid. But interestingly, while we were looking at the data set, we talked about how can we, when we're working with an imbalanced data set, what could we do? So we actually just brainstormed a couple of strategies, which we thought that we might explore in the future, but we wanted to jot it down first, so that we don't forget to have a look at these to see how effective they are. In this notebook, I'm not going to be using any of these strategies, but it was just a good exercise to just jot down these notes. So one of the things that we could do was resampling the data through upscaling or downscaling.
Yeah.
Harriet, do you want to explain what upscaling and downscaling is?
Yeah, yeah. So I think the resampling method is one method to tackle the imbalance dataset problem. So for say, because like for say you have in this case probably like 80% of the data are in the normal class, and then the remaining 20 is in the horrible minority class. So therefore, the minority class is not really getting a good representation in training the model. So therefore, a lot of the times that people chose is to upsample those minority class examples. So some people, if your data is really big, so sometimes they just pick a very straightforward one, just duplicate every minority class to increase the speed of the production model. But then if you want to be more complicated, so they also have different resampling schema. So for say one is called mode, so synthetic, majority, something class, something sampling. You can look that up in Google for sure, because it's a very popular data set. And then there's other thing too, so you can do downsampling. But the drawback of the downsampling method is that when you are downsampling the majority class, so sometimes then you actually lose some information when you train the model. So that's one cost. But if you like have a really, really, really big data size, so that's also that's also one method that sometimes people chose to use.
Hmm. All right, and then yeah, there are also other methods which at this point I think I'm just gonna skip. So if you're interested, check out the notebook for all these strategies, and then you can try to Google them afterwards. So the next step, what I did here is just basically, so this is the compression step where I turn all the ones, the all or the non-ones, the 2, 3, 4s, and 5s into a
Yeah,
0.
yeah.
So, and I also name the column target
Mm-hmm.
because this is what we're going to be using at the very end, right? At the very end for the training for the classifier.
Yeah.
And then here, I'm preparing the data sets. So the first thing I do is I separate the data into the two classes. And the reason for doing that is because, well, obviously we have two imbalance classes.
Yeah.
And it's important that if we just randomly sample them and split them into the validation set, test set, training set, the training set might have a lot more. Uh, the training set might have a lot more. Let's say class 0 versus the test set, and that's going to cause a problem when we're when the data is skewed. So we want to make sure that every single set, the training, the test, the validation set, they have this equal percentage of
Exactly.
of
Yeah.
the same, yeah, of the two classes.
Yeah.
So that's what I did here. And then, so now at the end, what I have is, let's see.
Can you show which line of code actually does that purpose to make sure the class representation is the same in the three separation of data sets?
Sure. So you see here, this is where I select. This is where I create the condition for when the target is 1.
Yeah.
When it's non-negative, it's not 1. And so in here, I split them up into two different sets, right? So I have the negative reviews and the non-negative reviews,
Mm-hmm.
right? So
Yeah.
so after that, I take each set. I take the negative set. So
Mm-hmm.
here is a negative set, and
Yeah.
um, and I split it into 20%, 20%, and 60%. So as you can see here, the validation percentage and the training percentage are the same. There's 20%, and I give the remaining to the training set. That's how I end up with 20-20-60 split, right, for the non-negative. Sorry, for the negative first, and then the next thing I do is I do it for the non-negative, and then I just concatenate them together. Yeah.
Great. Yeah. Perfect.
So in the end, what we have is, as you can see, the validation set, I have 20%, the training set, we have 60%, and the test set. This is just a sanity check, just to make sure that, I'm not double counting, and I basically end up with the same number of reviews as I started with.
Yeah.
The next thing I do is I'm using the fastai API. So there's this thing called the text LM data bunch, which stands for the text language model data bunch.
Yeah.
And I feed in all the different data sets that I created, the training, the validation, the test set.
Yeah.
And I tell it that the text column has the column label text, and the label columns have the label target.
Yeah.
And then you can see that this is just an example of that, right? And one thing to notice is that when I call show batch, after I created this text language model, only the text column is being shown. So the label doesn't really matter, because look, we're trained the language model here. So what we care about is the entire corpus. So the label, whether it's positive or negative, doesn't really matter, because what's happening behind the scene is that we're fine-tuning the weights.
Before the encoder part.
Right.
So the class doesn't come in. Yeah. Exactly.
Right. So what behind the scene, what it's doing is basically trying to train, create this language model, which is Yelp Review specific.
Yeah.
I wonder what sort of like Yelp Review specific words would be there. Maybe something like the presence of food. I don't know, tomato juice. Well, I guess Wikipedia. Yeah, I don't know how often tomato and juice would come out in Wikipedia Wikipedia text.
Yeah, actually, so when I was actually watching the fastai video lecture, they actually say you can actually use the same method on more domain-specific data set. So for say legal data set is one example. So even though that even though like the legal, like for say the tokens, the words actually is not in the encoder, the pre-trained model that you downloaded, but because in the encoder, in the pre-trained model that you downloaded, there's one embedding layer, right? So that embedding layer, it's a matrix, and then it has vocabulary, right? So there are some unknown tokens, like the model, pre-trained model actually doesn't see. So what they do is they actually create an unknown token for that embedding matrix. So what they do is they actually incorporate that unknown token into the thing. And then firstly, they use the average. So the embedding matrix, every row is a token, right? And then that row is just a vector representation for that token. And then they start initially as the row average for that unknown token. But when you actually fine-tune the model along the way, when you're doing the fine-tuning language model, then that row vector for that unknown token that pre-trained model hasn't seen will get readjusted. So that's why they actually say, like for say when you are training this language model on legal text, the accuracy of the language model for the domain specific is actually getting much higher than the general corpus. Like for say when we are fine-tuning Yelp dataset or like these IMDb dataset, usually when you see after the fine-tuning of the language model, the accuracy you get is around 30%, right? Is that what you
Yeah.
see? But for say for some domain-specific data set like legal, sometimes you can get 80, 90% accuracy for just the language model part, because I think that's why because it contains much less noise than the
Yep.
general purpose. So therefore, it's easier to predict. It's more predictable, like what you're gonna say, because this is a sequence model, right, for the language model.
Mm-hmm.
So that's why I think it's okay if it doesn't exist in the pre-trained vocabulary. It's my just my thought.
Yeah. So I can actually show you actually what happened, like what's the percentage. So yeah, so basically after I created the data bunch, I save it, and then the next thing I do is I create what's called a text class data bunch, and this is for the second task that we're trying
Yeah.
to train on the classification task. So, and then as you can see in here, this is when the target column comes in, because this is when we actually care about the target for the review. So the target is basically the rating, right? The rating, whether it's a 0 class, which is non-negative, or a 1 class, which is negative. And so let's see. So now here is where the language model is being created. So the language model learner, this is basically behind the scenes generating a language model learner at the behind the scenes, and we use learn.lr_find to find the learning rate. And in this case, we see that the learning rate, the loss is the lowest around 1 to the 1 times 10 to the minus 1. So usually we try to just
one back.
yeah, this is like highly intuitive. So this is we just try to pick something that's not the lowest, but that's continually going down. So in this case, I'll probably just pick something like 1 times 10 to the minus 2 right here, or even, I don't know, like 5 times 10 to the minus 2. That's fine.
Yeah.
So that's what I picked. And here we can see that the accuracy is about 27. Yeah, but the main thing is that the main thing is this is after 1 cycle. So
and this is also before you unfreeze, right?
Yes, this is before
I
unfreeze.
Yeah.
So what I do is I save it. So this would be fine tuning just the final layer, right?
This is no, because the final layer, like the decoder, we are actually not touching it yet, right? So we're just fine tuning the encoder part, the language model part, right?
Yes.
Yeah. So I think this, I have to go more detail into it, but I think this, because this basically just like freeze all the layers of the language model. It's probably, the only fine tuning the last layer.
Okay, so and then generally after we run a cycle, run any learning cycle, we would do a save just to have some intermediate results. And this is where you'd find that if you connect it to your Google Drive, that this is where it would be. This is where it's being saved, because when you're using Colab, when you destroy this notebook, well, destroying meaning like even when you close this, the session is gone. So it's important for you to save your model if you want to save some time, so that you don't have to run like every single
Yeah.
cycle. So next time you can just come in here. You can just skip this this part and just
Yeah.
go straight here to load, and that will speed up uh, the running of your notebook.
Yeah.
So yeah, so and then here is where you see the language model being unfreezed.
Yeah.
And this is where we train 10 cycles. So
Yeah.
or 10, yeah, 10 epoch, 10 epoch.
Yes.
And so you can see the accuracy, like Harriet said before, it's around like 28%. It's sort of just hovering slightly below 30%, which is actually not bad,
Yeah.
considering that it's such a general corpus, right? So
Yeah.
anyone can write a review. It could be on a restaurant. It could be on many different, like you can be on an accountant. It can be on different types of businesses. I
Yeah.
think it's, yeah, I don't know whether they filter that for the data set for the 100,000 reviews
Yeah.
that
And
we have.
also one thing to add is also like when you're unfreezing the model, you notice that when you're actually training more cycles, your learning rate is actually one magnitude lower than your previous frozen learning rate, right? So and also because like as Johnny mentioned, like here the accuracy actually started to decrease like after epoch 5. So usually that's what happened when your validation set loss function. The loss actually starts to increase again. So usually when you train different epochs, you see that your validation data set loss function actually will decrease up to until 3. But when it starts to increase again, it means that your model has been overfitted.
Mm.
But you can see that actually your training data set loss function keeps dropping, right?
Mm-hmm.
So therefore, it just says that when your model tried too hard on the training set, but
Yeah,
then
it feels like it's remembering. It feels like it's trying to remember the training set now, right?
yeah, exactly. So then not up to a point that it's not being able to generalize enough for test set.
Mm-hmm.
Yeah, that's one thing.
Yeah, but I think this is like somewhat, when I look at the accuracy here, is somewhat in line with IMDb, like movie reviews.
Yeah.
So it's still pretty good. And then again, I would save the fine-tuned language model.
Yeah.
Again, this will save time. And then yeah, so this is an interesting part, which I think we can make it a little interactive here. So after we have the language model, we can actually try to see uh, if we can generate some interesting text here. So what I did here is I already ran this. So I give the model something to begin with, right? So I say I love this location because, and then it'll tell me that it's close to my house and the friendly service on the other hand is great. So I mean, it's still not like perfect English, but you can see this is like this. You can sort of imagine this is what would happen in a Yelp review or in a Google review, right? It talks about the friendly service. It talks about close proximity to my house. So I mean, it's actually it's pretty good, right? Like it talks about the parking. The parking is quite crowded though. The indoor seating makes it very close to some stores that's only open, right? Like, yeah, it's starting to get to some nonsense, but I mean, for the first couple of bits, I mean, we're actually seeing pretty good results, right?
Yeah, even making grammarly sense, right?
Yeah, I mean the punctuation is a little wacky, right? Somehow there's like a semicolon that pops up, but I mean in general it's not complete nonsense. It talks about the coffee, the fish, the chips, our average, very very typical of reviews, right? So it's kind of cool. So do you want to fill this in to? Do you want to like start try to give another phrase just to see what we get?
Oh, I don't understand Shakespeare.
Wait, I need to know how to like escape this properly. I think it's gonna struggle.
Now let's see what it produces.
Oh, I think I'm supposed to give it a space as well. What's happening?
Oh, you have two quotation.
Oh yeah, because because the don't.
Yeah.
Got a temperature. What? Oh, so what was the 100 before? The 100 was. Oh, so yeah, right. So it was like this before. So.
Yeah, that works.
Right? Is that? Wait, does that look? Wait.
Yeah, that's good.
Yeah, that was like they didn't have many options, right? So they had a bunch of beers I've never heard of before. So.
Really? They don't even have a
Wait.
Temperature. Oh,
Some
temperature.
Oh,
I think
too many, right? Like they weren't like 6, so.
right. So the first one is the item, and then return x predict. Temperature is not here.
how about I say I do? So let's just skip the quote, the escape. Yeah.
Oh, right, yeah. So I think.
I do. How about I do? And then let's just try this to see if it works.
Wait, hold on. So let me just, I think I have this line somewhere. I think I can, yeah, I think I can just copy it from somewhere else. So.
They probably got confused about the regex escape.
Oh, okay.
Let's see without that if it
Wait,
works.
hold on. Let me just turn on the lights. It's getting pretty dark in here. Okay. Okay, where is it? So, let's see. Is it here? I think I was working on another notebook here. I think I just can just like quickly copy and paste the line because I'm not very familiar with the API. Yeah, so it's it's the same. So I wonder how come like.
Yeah, because yeah.
Wait, was the learn executed above? So 28 seems like it works.
Yeah.
And here.
It was complaining about the temperature parameter, right? Key argument. Temperature.
Keyword temperature. Because I
think we will debug this for. We will give an update next session.
Yeah. Okay. Right. But I wonder whether this can. Okay. So so let's try to continue on. Yeah. So So this is, yeah, so this is the fine-tuned encoder, right? So after I've done that, I can just do a save again,
Yeah.
because now I fine-tuned encoder, and now we're on to the next step, which is taking that language model and training this supervised learning task. So again, I take the training, the validation, and test set, and supply the text and the target, and there's one more argument here, or parameter that I'm passing in, which is the language model vocabulary. So because we've trained the language model, so we're getting the language model vocabulary into the class so that we can actually use something that we've trained, or else it's not going to make any sense. This is basically a vector of all the words that are in the model. So once we do that, we can again save the data bunch, save the text class data bunch, and we can now create a text classifier learner. And so this is very similar to what we trained before with the LR find. Again, we use LR find to find the learning rate. So this is a little bit closer to let's see, this is, what is this? This is like 1 to the minus 1, 1 to the minus.
Yeah, I think it's probably the 1E0. Yeah. So I feel when you actually train your first cycle, you probably want to pick the 1E minus 1, right?
1E minus 1. So here, yeah. So 1E minus 1. Yeah. Yeah. So I probably pick something that's too small.
Yeah.
Yeah. But in any case, it got a 93.8% accuracy.
Yeah, that's great.
Yeah, and yeah. So again, I saved that, and that's my first attempt, and nothing is actually. So did I call unfreeze?
No, I think that was the first train. And then, so everything is frozen all the way up to the last layer. Then when you call freeze 2, then it means that you unfrozen the last 2 layers.
Right. So I unfroze. Yeah.
Everything still kept frozen all the way.
Right.
Yeah.
Right. So now I'm sort of moving backwards in the neural net, right?
Yeah. Can you explain how you chose this learning rate to slice?
Yeah, this is the difficult part. So when I was watching the video, the fastai video, I think Jeremy explained it once. Oh no, someone was asking a question and he explained it, and I already forgotten about it.
Okay, we will give this update next session too.
Yeah.
Yeah, so this I think this is what they call the gradual unfreezing of layers to train, right? So it's one of the contribution in the paper that Jeremy wrote about the universal language model fine-tuning for text classification, right? ULMFiT. Yeah.
Isn't that wait, hold on. This is the learning rate, right?
Yeah. So, but then like the freeze and unfreeze, this framework of fine tuning the model is one of the 3, I think, contribution in the paper that Jeremy wrote.
Okay.
So this gradual unfreezing plus the learning rate schedule, so the cyclic learning rate scheme So that's the second, I think, contribution of the paper. And then there's the third contribution. I think I cannot think of it on top of my mind now, but we can give that update too. So now we have 3 updates to give for the next.
Right.
So keep tuned.
Okay, so so as you can see, the accuracy actually increased quite a bit, right? So from wait, so it went from did it? So it went from 93.6 to 94.7. Oh, but this is actually after the third unfreeze. So now we're going back another layer. So we're going back a third layer.
Yeah. Usually I just unfreeze everything after the last 2 layers.
You just unfreeze everything after those 2. Okay.
Yeah.
Right. Because because the weights wouldn't be updated so much, right? After after your initial first 2 fine tuning.
Yeah, because usually the decoders usually compose like 2 or 3 layers, right? So after like 2 or 3 layers, like basically, which means that you've fine-tuned the whole decoder part already. So then you just kind of unfreeze like the whole model to fine-tune. That's my interpretation.
Yeah, well, I mean, basically it's all here.
Yeah, exactly. Yeah.
So, pooling linear classifier. So we have a linear layer.
Oh, it's more than 2 layers in this decoder.
Yeah, then there's the batch one.
Yeah.
Yeah, so I wonder, so when I was doing this, I wonder how far you can go back until you hit a point of diminishing return. Yeah, like can I continue to do this until I unfreeze -10?
I feel like at one point you just unfreeze everything because the decoder part mostly it's the linear, it's the feed forward layer, which is the last layer, the linear, and then it's the drop, and then it's the drop out layer, and then the rest is I think kind of like you can fine tune them together. And then it's to a point that you see that your valid loss just doesn't improve much.
Yeah. So so basically when Jeremy did his example, he unfroze 3 times, 3 layers until he unfreezed the whole thing, right? So as you can see here, and then he did 10 epochs, right?
Yeah.
Yeah. So with the classifier here, you can see at the end we're hitting, around 94.7%, 94.8%. But again, right, you can see that the training loss is actually going down all the time, but then the validation loss is actually starting to go up.
Yeah.
So it's sort of start to feel that it's starting to overfit, right?
Yeah, exactly. Yeah.
Yeah. So ideally, probably, so it's going down, and then starting to go like creep up a little bit. So I think ideally it will stop around like the 3rd or the 4th epoch.
Yeah.
You can continue to train this for another 50 epochs, right?
Yeah.
But then the problem is now you're completely overfitting this model here.
Sometimes actually when you see temporary loss increase doesn't really mean that you overfit. Sometimes it could be just that in your last surface plot that you actually reached a local minimum. But then when you actually increase the epoch, it actually helps the iteration to jump out of the local minimum, but for a temporary increase of the loss function, but for a long-term long-term decrease of the loss function so that you can find your global optimum.
Mm-hmm.
So sometimes a temporary increase of the loss function may not be really a bad thing. It may be just in the process of skipping that local minimum.
Right.
Yeah.
I think the difficulty is trying to figure out when is which case, right? That's usually the hardest part when I'm looking at these just as a wall of numbers.
Yeah, exactly. Yeah.
Yeah. So in here we can sort of try to play with this classifier, right? So what I did was I tried a couple of like fairly basic examples. So here the food is great. You know, I said the food is great here, and it gave me a category 0. And then, oh look, this is a false positive or false negative.
It looks different from last time that you show, right?
Yes. So what about if I put something like horrible?
Yeah, false negative. This is a false negative.
Horrible service. Oh, it's actually not even doing its job.
Yeah.
So I wonder what. Very bad service. No. Oh no, it's not even.
Yeah, so in this case, the accuracy can be misleading, right?
Yeah, because we have a imbalance.
Yeah, imbalanced data set. So we might need to actually use add more metrics. So in this case, we should probably add precision and recall to this metric. So then you can see how many true positives that you actually got. Yeah.
So it's probably something we can do next time. To add it into. Yeah. Wow, this is actually like pretty bad. Like the model that I trained before, it's quite a bit better than this one. Like if I put something like I don't know, like you should not get food here.
So do you remember what did you change then to from last time?
Oh, that's a good question. So you see, it's one of the things, maybe this is a learning for me, is to figure out a way to really reproduce these things. So what did I change? There isn't much that I changed.
Yeah, so I feel this is like the really the fine tuning, like the different cycles really matters, really affect significantly your result. Yeah. Probably just change like the learning, no, not like the number of epochs, maybe.
No, I didn't change the number of epochs.
But learning rate, did you change maybe learning rate, the maximum learning rate?
Yeah, there shouldn't be. Oh, I think, well, here's one thing which will lead to this being different every single time. So you see this random permutation. So I guess a learning here for me next time is to make sure that I have a seed so that I can always create the same permutation.
Yeah.
So with this here, it means that every single time I run this notebook, it's gonna pretty much give me a different result.
Yeah, exactly.
Yeah, is that what you do? You would seed this random number generator?
And there's another function in scikit-learn that we can borrow to actually ensure this purpose. The train test split, that function that we can borrow from sklearn, and then there's a parameter called stratify equals. So if we specify stratify equals the response class, then it will make sure that it has the same proportion of positive negative class in both training and validation set.
Right. Yeah, I guess that sort of shows how sometimes delicate these things can be, right? When you're training.
Yeah, it's very subtle.
Mm-hmm. So we've been going at it for a while. Should we end it here?
Sure, yeah, so there are 4 components that we will provide the update next time, right? So we will recap that. The first one is when we are actually using the predict function, the API, the keyword temperature, we need to figure that part out. So that's the first update we will provide. The second update, do you remember?
The second up, no, we should start like.
The second update is the slice. So what is the mechanism for slicing this learning rate? That's the second update. The second important update we will provide as well. And then there's the third update is up to when we should freeze, unfreeze up to start before unfreezing the whole thing. So I think these are like the 3 at least major things that we will provide an update on.
And the link to this notebook will be shared in the description of the video. So and I'll make sure I add a seed in here as well, so that this is a reproducible notebook.
Yeah, so you can subscribe us and then provide your comments and then share about your experiences under this video as well.
Great. And what are we gonna do next time other than?
So we are also gonna compare BERT with this.
Right. So we have to integrate BERT's encoder. Well, how is this gonna work? So right. We're gonna have the BERT pre-trained model.
Yeah, instead of the AWD, LSTM, wikitext 103. Yeah.
Right, and we want to see if we can beat this this result here.
Exactly.
Yeah. All right.
Great work. So yeah, people share your comments and then just give us some advice if you have anything to add.
All right.
Okay, happy coding, everyone.
Happy coding.
Yeah, it's fun stuff.
Yeah.
Okay, so great. See everybody next time.
See ya.
Bye.